Hello, everybody, and welcome to an introduction to GIS. So my name is Jay Border, and I manage the Maps Data GIS department in the McMaster University Library. So the purpose of this presentation is to provide you with the fundamental background information you need in order to succeed in your upcoming assignment. So I've split this content into two presentations, and this first presentation is going to cover an introduction to geographic information systems and cover the basic fundamentals of GIS, geospatial data, and geospatial analyses. The follow-up presentation will give a hands-on introduction to quantum GIS, or QGIS, which is a software that you'll use in your assignment. So by the end of the assignment, it's expected that you'll be able to describe the components and basic functionality of GIS, as well as communicate its range of uses, demonstrate that you have basic operational skill, and hopefully make some effective and very attractive maps in the course of developing a skill that you can use in future endeavors, whether it's in your schoolwork or in later jobs. So what is GIS? So GIS itself stands for Geographic Information System. And so what that is a system able to assemble, store, manipulate, analyze, manage, and present geographically referenced data. And what we mean by geographically referenced data is that data that's associated with or identified by their location. So GIS can also be considered a digital representation of real-world geographic features, and in that representation includes some information about its location as well as its attributes. So any descriptive information or contextual information that describes what's at that point, as well as information about spatial relationships between features. Commonly, we use GIS to refer to the software itself on which we're doing the analyses, but in fact, a fully functional GIS has 5 different components. And so it's not only the software that we run the analyses, but the hardware upon which that software runs, as well as the data that we use in those analyses, and the applications and methods that we use for those purposes as well. Last but not least, GIS also includes the people. So whether they're involved in development, in creating new software or new applications or methods, or they're the users that are taking existing data and creating new knowledge. So a very brief history of GIS is that it's made in Canada. So it's the first instance of GIS came in 1960 and was developed by Dr. Roger Tomlinson, working for the Government of Canada, in order to manage the Canadian land inventory data. So this system was called the Canada Geographic Information System, or CGIS. In the decades that followed this, in the 70s and 80s, we start to see much wider adoption of this and an expansion into different fields. We also see the development of a number of commercial and open source software. So this is where we see software such as CAD, Esri, MapInfo on the commercial side, and MOS and GRASS on the open source side. Throughout the 90s and the aughts, we see rapid growth and extension of use. So we see expansion into non-traditional fields. And so visualized on a timeline, what we can see is that was started in its early years as being used primarily for government use in managing natural resources, oil and gas, forestry, mining purposes, to the current day climate where it's used in all sorts of different applications, whether for government or commercial purposes. So everything from banking to retail to public safety, public health, and law enforcement. And if we think about our day-to-day lives now, we carry around smartphones that are giving information about our spatial location all the time. And a lot of our apps that we have on our smartphones rely on knowing where we are in order to operate properly. So what's so special about GIS? Well, if we consider it together with a suite of products and think about this concept of geospatial technology, we start to understand the power of geographic information systems. So considering global positioning systems, or GPS, which give us information about our location on the surface of the Earth, and then also thinking about remote sensing, which provides us ability to observe, measure, and classify features on the Earth's surface. Once we can take those pieces of information together and manage, manipulate, and disseminate them with a geographic information system, what we get is geospatial technology, which is being heralded as one of the three mega technologies for the 21st century. So alongside nanotechnology and biotechnology, and the promise of this technology is that and I think this is something that we're seeing right now, is that it's changing the way that we govern, the way that we operate in terms of commercial business, and how we live our everyday lives. So there's a number of different ways that GIS might be used to solve real world problems. And here's a couple different examples. So we may be interested in doing what's called a multi-criteria analysis, or using GIS for decision-making purposes. So we may have a question that requires that we have spatial information on a number of different variables, and we need some way to bring all that information together in order to classify different areas in terms of its suitability for a purpose. And so for this example, we're seeing a multi-criteria analysis used for understanding the potential for grazing in Australia, where all these different factors have been brought together and ultimately combined so that it can be used for decision-making purposes. We may also use this in geostatistics or geophysics applications. So we may have remotely sensed data for an area of interest. And so we can use GIS to help us interpret that image in order to extract trends and certain features out of there that may help us in our endeavors to collect natural resources or manage natural resources in a given area. GIS also gives us very strong database functionality, so we can compile diverse sets of information and data, and we can search, query, and retrieve this data from databases when we need it. It's also very powerful for visualizing data. So a very important part of geospatial analysis is visualizing what you have and using that as a means of asking new questions, developing new hypotheses, and pursuing those questions later on. GIS is very powerful for that purpose. And we also know that maps themselves have quite a bit of power in terms of communicating information to an audience. And so by being able to create maps with GIS, we can convey information very efficiently, and we can also engage our audience with if we are able to produce an attractive and compelling map. And another thing we've seen increasingly over the past decade or so is the use of GIS in historical analyses. So taking historical information, tying it to the surface of the Earth, and then using modern GIS approaches to come to a better understanding of historical features, historical events. So there are many different types of GIS software that are available, and I think the take-home message here is that there are different tools for different purposes. So some are fully featured, some are very specialized, some are open source and completely free to use, where others are closed source and licensed. Some are very user-friendly and designed to be so. Others are quite highly technical and take quite a bit of time to learn. You may find some software in online form and then others in standard desktop. The software that we're going to use for the purpose of your assignment is called Quantum GIS, or QGIS as it's more commonly referred to. QGIS is a free and open source GIS software, so it's not going to cost you anything. You can install it on Mac, Linux, and Windows, which is really nice. It's a very user-friendly interface, fully functional, and relatively lightweight as well, which is nice. This is built as part of the Open Source Geospatial Foundation. So the OSGO maintains a number of different GIS software, and they integrate them together as well. And I don't know if you'll get a chance to see that in QGIS as you work with it, but there are a lot of linkages to other GIS software packages that provide a lot of functionality. The software itself is built in C++, but uses Python for scripting and plugins. So if you're familiar with Python, you can actually script a lot of your analyses if you want to automate that process. Version 1.0 was released in 2009, and the current release is version 2.16, with the long-term release being 2.14. So if you have 2.14 or 2.16 installed, you should be good to go for the purposes of this assignment. All right, so next we'll talk a little bit about the fundamentals of geospatial data, and this comes down to how do you represent real-world geographic information on a computer. So the first thing we'll talk about is different data models, and data models are ways that we represent real-world features in a digital format. And so the most common methods that are used for this purpose are vectors and rasters. So in a vector data model, we can represent features as either points, lines, or polygons. So points are singular features with X, Y, and sometimes Z coordinates. And some features that we might want to represent would be hospitals or other buildings, measurement points, cities depending on the scale. For lines, there are a series of connected points, and some common features we'd represent with that would be rivers, roads, transects, etc. And polygons are areas that are enclosed by self-connecting lines. So you see this progression here where points are singular items, lines are a collection of points, and polygons are lines that close in on themselves. And so polygons we may use to represent things like lakes, countries, buildings, and cities again, depending on the scale. If we are zoomed into a city and we want to represent the extent of a city, we may use a polygon instead of a point. So vector data is useful when we have clearly defined objects, and it's very nice because it also gives us information on the spatial relationships between items. But as I alluded to before, which type of vector we use can be very scale dependent. So on the other hand, a raster data model represents data with a regular grid of cells. And so each cell has a specified ground area, which relates to what's called its spatial resolution, and values are assigned to these cells. And these values may be categorical in nature, so we may be indicating some sort of land use, some sort of classification on another scale, or they may be some sort of continuous value. So we may represent in every cell an elevation for that point or a temperature for that point. So for example, satellite imagery provides us with a raster, and within every cell we might have information on the red, green, and blue color within that raster cell, which gives us what we know as a normal image. We may also have digital elevation models, which gives us elevation instead of red, green, blue information. So raster data comes in a number of different formats, and we may use it to represent different features or convey different information. So rasters and vectors relate to each other in that we can use both models to represent features. And so here's an example where we can represent a certain feature as a point or as one cell in a raster, similarly with a line and with a polygon. And so the choice is up to us and our purpose, which model we use to represent this. All right, and so for each point, if we just had the XY coordinate of a given point or a line or a polygon, we don't have much other information about what is at that point and why it's important. And so we offer that information through adding attribute information to that point. And so the attributes link the non-geographic data to geographic data, and they provide supplementary and contextual information. So in this example, the point that we've highlighted in blue here is a singular tree. And in the attribute table, we can see that we've added contextual information about what is at that location. So we know that it's a white pine that's 10 years old and its health is good.